My name is Erin Bodwin, and welcome to video 3 in my 3-part series on light. Everything we know about objects in the universe that we have never been to is based on two things: the light it emits and the gravitational force it has. So, for example, from the light a star emits, we can tell how big it is, how far away it is, what it's made out of, how hot it is, how it's moving relative to us, if there are any planets around it, and how long it will live. There's a way scientists categorize stars called the Hertzsprung-Russell diagram. It graphs a star's color, which tells its spectral type or surface temperature, versus its luminosity, its intrinsic brightness or magnitude. On it, astronomers plot stars' color, temperature, luminosity, spectral type, and evolutionary stage based on the light they emit. There are 7 main types of stars in order of decreasing temperature: O, B, A, F, G, K, M. Most stars, including our Sun, fall under the long slope of main sequence stars. These stars fuse hydrogen into helium, which is called nuclear fusion. The hotter they are, the brighter, and they are currently at the most stable part of their existence. Red giants are stars near the end of their life cycle. When a star runs out of hydrogen to fuse into helium, its core contracts and its outer layers expand, and it'll eventually explode, becoming a planetary nebula or a supernova, and depending on the mass, it could become a white dwarf, a neutron star, or a black hole. Small, cool stars like our Sun will become white dwarfs and fall below the main sequence to finish their life. Some larger stars during their lifespan will fuse more than just hydrogen and helium. They'll fuse heavier elements too. Elements like carbon, oxygen, magnesium, neon, silicon, sulfur, and iron. This is how a lot of elements in existence were created. Other elements came from supernova explosions. So technically, we are all made out of recycled star stuff, which is kind of cool to think about. A star typically needs to be 8 to 15 solar masses to become a supernova when it explodes, and 25 solar masses to become a black hole. So we tell how stars or entire galaxies are moving relative to us with what's called a redshift or blue shift. In the first video, we learned that wavelengths get shorter moving toward the blue end of the spectrum and longer moving toward the red end of the spectrum. And there's 2 main types of redshifts. There's the redshifts from the expanding universe, the accelerated expansion of the universe, and then there's the redshift from planets and galaxies just relative to each other. So when something is moving away from us, like a star, its spectrum gets shifted red. And if a star is moving toward us, its spectrum gets shifted blue. But since everything is accelerating away from each other at the same time because of the accelerating expansion of the universe, then that has to be accounted for when calculating a star's motion relative to us. Another way to understand redshifts and blue shifts is to apply the same concept to sound with what's called the Doppler effect. So if you've ever heard an ambulance coming towards you, you know that the siren sounds like it's getting higher and higher pitched. This is the sound waves in front of the ambulance compressing, whereas after the ambulance passes you, it sounds like the siren is getting lower and lower pitched, and this is because the sound waves behind it are expanding, and the same thing happens with light. Thank you so much for watching my 3-part series on light. I hope you enjoyed.